Good morning. Hopefully you guys are doing all right after a 3-day weekend. So let me do the usual stuff. Let's see here, 1 second. What was I looking for? Where'd you go? Sorry, I got tons of things on my computer here. Here's the usual things, the attendance and the tutoring and the end of quarter evaluation, which hopefully, I don't know if I can actually see if you guys have done it or not. I'll have to go check that out and ask Sarah. Mary myself know actually. Ask Sarah. But please go do the eval if you, not if, please go do the eval whether or not you want to. I would appreciate it. It shouldn't take too long. It's not too many questions. What was I going to say? Oh, there was something. Okay, there's a million things on my mind. We'll get going here in a minute, but I know what I wanted to ask you guys. So sometimes when you guys write stuff in the Google assignment, the weekly participation points, I write comments back. Are you guys seeing those when they get returned to you? I know some of you here today. I definitely wrote comments back to you, and then so yeah. Do you guys see those comments when I return those assignments? Okay, great, awesome. That's what I thought, but I just wanted to make sure. Also, I'm the same question for the weekly reflections. I assume you guys see the comments I write back, especially when you guys write funny jokes or memes. I definitely appreciate those a lot. I assume the answer is yes. So let's see here. I'm going to go with yes. There's the links to the attendance and tutoring again. Before we get going today, I just wanted to share my weekend with you guys because I had a good time. So I will share some pictures with you real quick. If I can remember, yeah, share my screen. Here we go. Just do that. Share. So I went rafting on the Cache Creek River this weekend with Sarah, who I imagine most of you know, and her husband and her son. And here's us rafting the river, which was a lot of fun. And that's not the picture I meant to go. There's a picture of me looking really excellent. My hair is better than usual. And let's see, there's me wearing a hat, which was smart because definitely was warm out there and would have got sunburned. And let's see, there's me again. That's the same picture. And here's me at the camp wearing my hat and my jacket. Got a little cold. Anyway, just thought you guys might enjoy seeing pictures from real life and not just online all the time. So that's what I was doing this weekend. It was a lot of fun. It was good to get outside and do stuff. And yeah, so actually, let me see one thing real quick here. Okay. That was what I did over the weekend. And oof, definitely got banged up a little. I got knocked out of the boat a couple times and fortunately got pulled back in. All right, so today is the Mercs Day. I was looking over the Mercs material. Looks like you guys are covering a lot of stuff. Looks like covering. Oh, definitely, yes. I will tell Sarah. I see Sarah. So Sarah and Zach, who's her husband, and her son Liam, they're essentially our best friends. And so we decided that we are all quarantining together. We are one family during quarantine. And we see them all the time. I saw her this morning. I was having coffee with her. So I will definitely let Sarah know that she is missed. So let's see. Mercs, probability stuff, and arc length. So what do you guys want to talk about today? Do you have any specific questions? I definitely saw you guys wrote some things that someone asked, I don't remember who, to make some videos about the special distributions. I definitely can do that. We can also talk about those today though if you guys want. So what do you guys want to hear about? We can start with arc length. Sure. Arc length is, yeah, arc length is kind of a pain, but not really. So I mean, really examples are the best way to do it. So let me grab, I definitely have some examples good to go here. Where'd you go? Yeah. Okay. So I'll start putting video up here. For those of you in FAM's class, I really can't imagine you guys will cover arc length. Usually I don't think it's, I mean, big surprise, right? Usually I don't think it's covered in 16B, but that doesn't mean some people won't cover it. So here's how the formula for arc length works, which I assume he showed you already. Also, no, okay. So defining the length of a curve y equal to f of x on some interval from a to b. The way we calculate that is by doing the integral from a to b of the square root of 1 plus the derivative of this function. Oh, sorry, not the derivative, but the derivative squared. Apologies. Do I need to flip my video? Everything's backwards to me. Sorry, one sec. And I didn't look super closely at his notes, so I don't know if you guys, actually, let me take a real quick gander here, because I don't know if he's just doing it in terms of x or he's also doing it in terms of y. Let's see here, where do you go? Length. God, his notes are hard to read. It looks like just in terms of x. I mean, not that you couldn't do it in terms of y. Oh, he also did it. Oh, interesting. Okay. And surface area? Okay. All right. Well, okay. So here we go. So you can do it this way if y is a function of x. You can also do it if x is a function of y. Sorry, so if you have like, if you have some x equal to some function of y, it's essentially the same formula. It's just the integral from whatever to whatever of the square root of 1 plus your function's derivative squared dy. And then if you have them both as functions of time or t, right, if you have a parameterization, you also have this version of the formula, which is the square root of dx dt squared plus dy dt squared dt. So these are the various arc length formulas, and they're not usually terrible. Let's do an example. And most of the time, they're going to end up going down in one of two ways. Sorry, I had an example and then where did I put you? There we are. Sorry, I've got a million tabs open and there we go. Okay, sure. So let's look at some not terrible examples. So let's say I want to find the length of y equal to x to the 5/4 from 0, 0 to 1, 1. Okay, no, I can't see myself here. Not that I need to see myself, but I kind of like seeing myself. Okay, so one thing to remember about most of these problems, these arc length problems and surface area problems, is that they shouldn't be terrible. Meaning if the interval looks like it's going to be really hard, there's probably something that might be being missed. Also, here is the usual attendance tutoring stuff. So I'm just going to set this up. So the length is going to be the integral from, so it should be, in this case, if we're doing it in terms of x, right, y is a function of x, I'm going from x equals 0 to x equals 1. I know they're the same values either way, but it's important to remember that this is x equal to 0 to x equal to 1. The square root of 1 plus the derivative of this, so 5/4 x to the 5/4 minus 1 is 1/4 squared dx. Oh, I need to be careful here. because I picked examples from a class where we have different methods of integration. I might have picked something that's, so let's just say we're going to set this one up and then I'll think about actually integrating it. So here's how this would look. This is going to look like the integral from 0 to 1 of the square root of 1 plus 5/4 squared is 25/16, and x to the 1/4 squared is x to the 1/2. And I'm pretty sure this is something we don't have the tools to do. I'm not even sure if we can integrate this actually. Yeah, that's a tricky looking one. Let me see something real quick here. Sorry. One moment. Let me see real quick. Oh no, it's just the use of. That's a tricky use of. You guys talked, remind me, have you guys talked about back substitution in Merck's class? No, okay, great. So this one, this is how you set this one, but we're not going to finish this one. Let's do one that's more typical. So I definitely do know these next ones are ones that actually work out just fine. So a lot of the time, these arc length problems follow kind of a standard pattern. There's kind of one of two things that usually happens. So let's say we want to find something that's really shining brightly. I just got like a really interesting glare. Let's find the arc length of the function. What have we got here? Y equals x squared minus the natural log of x divided by 8 between 1 and 2. Okay, so let's just set it up. So the length is going to equal the integral from 1 to 2 of the square root of 1 plus, and you can kind of write this however you want. Sometimes people just write like the derivative, like this is going to be the derivative squared dx. So let's actually find the derivative. The derivative is, let's see, the derivative of x squared is 2x, and the derivative of the natural log of x over 8. So I'm really thinking of this as 1 over 8 times the natural log of x. So the derivative of 1 over 8 times the natural log of x is just 1 over 8 times the derivative of the natural log of x, which is 1 over x. I'm going to get a 2x minus a 1 over 8x. Okay, so here's the thing that's usually going to happen with these. When you square this out, you're going to end up getting a minus 1/2 in the middle. That's almost always going to happen. Watch. So 2x minus 1 over 8x squared. I can rewrite it as write the whole thing, or I could just use the pattern. 2x minus 1 over 8x times 2x minus 1 over 8x. And when we FOIL this out, I get 2x times 2x, 4x squared. I get 2x times negative 1 over 8x. The x's cancel, and 2 over 8 is 1 over 4. So I get a negative 1/4, and I get that twice, right? I get a negative 1/4 there, and a negative 1/4 there, which ends up being a negative 1/2 when I add them together. And then I get a minus 1 over 8x to minus 1 over 8x, which is plus 1 over 64x squared. Okay, the fact that there is a minus 1/2 in the middle is the key, because what's going to happen is we're going to add 1 to that, and then it's going to change from a negative 1/2 to a positive 1/2. So here's what we're going to get. We're going to get the integral from 1 to 2 of the square root of 1 plus 4x squared minus 1/2 plus 1 over 64x squared. That x squared is in the denominator. And then I'm going to add the 1 to the negative 1/2, making it a positive 1/2. So I got 4x squared plus 1/2 plus 1 over 64 x squared dx. And now here's the thing. I know that 4x squared minus 1/2 plus 1 over 64x squared factors as 2x minus 1 over 8x times 2x minus 1 over 8x. And here's the nice thing. This is the thing that makes this work. If it's 4x squared plus 1/2 plus 1 over 64x squared, it exactly factors as 2x plus 1 over 8x times 2x plus 1 over 8x. Right? If we multiply this out, I get 4x squared, I get 2x times positive 1 over 8x, which is a positive 1/4, another positive 1/4, and a positive 1 over 64x squared. So changing the middle term from a negative to a positive, which only happens when it's negative 1/2, right? Because if it's negative 1/2 plus 1, that plus 1 will change to a positive 1/2. So I really, really, really want to emphasize it only works if it's a negative 1/2 as the middle term. Then adding that 1 makes it a positive 1/2, and then it factors super easily. So this is going to factor as, or simplify it as, right? This is going to be the square root of 2x plus 1 over 8x quantity squared. And then we're going to simplify the square root of this thing squared. Now we should be a little bit careful here. It's technically an absolute value, and I would be really surprised if Merckx didn't mention that. So it's the absolute value of 2x plus 1 over 8x. But then we can drop the absolute value because 2x plus 1 over 8x is always positive on this interval. Right? If I plug in anything between 1 and 2, everything inside is positive regardless of what I'm plugging in, whether it's 1 or 2 or something in between. So I'm going to drop the absolute values. I'm going to reimagine 1 over 8x as 1 over 8 times 1 over x. And then I'm going to integrate this. I'm going to get the integral of 2x is x squared. And the integral of 1 over 8 times 1 over x is 1 over 8 times the integral of 1 over x is the natural log of the absolute value of x from 1 to 2. And then we've run out of room. Of course we have. I'm going to go up here because I really don't want to. Yeah, this is kind of just the general formula here. Evaluating that, so you get x squared plus the natural log of the absolute value of x over 8 from 1 to 2. Then we just plug it and plug in 2. You get 2 squared plus the natural log of 2 over 8. I'm not writing the absolute value of 2 since 2 is already positive. Minus plug in 1 and you get 1 squared plus the natural log of 1 over 8. But the natural log of 1 is 0. So I get 4 minus 1, which is 3, plus the natural log of 2 over 8. The thing I think that's most interesting about this, and also the most kind of annoying, is that for these ones where you do the minus 1 half in the middle like this, you essentially do all this work to end up almost exactly where you started, right? We took the derivative of this, we squared it, we added 1, we took the square root of that, we integrated, and once we did all that, we got back, and the integral was x squared plus 1/8 natural log of the absolute value of x. And that is very typical for these kinds of problems. You end up doing all this work and you get back to an answer where the integral is almost the exact function you started with, which is, I don't know, maybe disappointing. To me, it always feels like we had to do all this work to get there, and yes, we have to do all this work. So let's do another example. We'll do 2 more examples, maybe 3. But a lot of these ones where you have like 2 kinds of powers of x or powers of y added or subtracted together, it's usually a pretty good bet that the same kind of thing is going to go down. So let's do this one. And you can do it in terms of x or in terms of y. It really doesn't matter. Let's do one in terms, let's do x. Let's say I have y equal to, what do I got here? X cubed over 6 plus 1 over 2x. So again, I want to find the arc length on the interval from, what have I got here? X equals from 2 to 3. So just for you who just joined, we're talking about arc length, and here's the usual attendance and stuff. Please do fill out the attendance. So if I'm finding the arc length, I know I'm going to have to take this derivative and square it out. I kind of like to do that work before I start writing all that down. So let's take the derivative. And again, I might actually, before I even take the derivative, rethink of this as 1/6 times x cubed plus 1/2 times x to the -1, just to make it easier to differentiate. So taking the derivative, I get y prime equal to, let's see, 1/6 times 3x squared, and then I get 1/2 times -1 times x to the -2, so I get negative, I guess, that would be the best way to do this, -1/2 x to the -2. And then I would probably rewrite this as y prime equal to 3/6 is 1/2, so I get x squared over 2. And here I get -1/2x squared. And here's what I can already see is going to happen. When I square this thing, when I multiply by itself, when this term multiplies this term, we're going to have the powers of x squared canceling. So it looks like this is going to work in the typical sort of way. Let's find it. So y prime squared is going to be x squared over 2 minus 1/2x squared. You can use, so I like to write it out, but you can just say, it's the first thing squared minus 2 times the first times the second plus the next thing squared. Or you can write it out. So x squared over 2 times x squared over 2 is going to be x to the 4th over 4. And then x squared over 2 times -1/2x squared. The x squareds cancel, and the 1/2 times the -1/2 is going to be a -1/4. I get a -1/4. I get another -1/4 multiplying these together. That's going to be my -1/2. And then this time, this is going to be plus 1/4x to the 4th. Okay, so now I think we're good to go as far as writing out the integral. So the arc length is going to be the integral from 2 to 3 of the square root of 1 plus y prime squared, which is this. So I'm just going to write this in here. It's x to the 4th over 4 minus 1/2 plus 1/4x to the 4th dx. And I might, at least for myself, be like, oh yeah, right, that's my y prime squared, or your dy dx squared, or your f prime, whatever notation you want to use there. And then we know that when you add the 1 plus the -1/2 makes it a positive 1/2. This is going to be the integral from 2 to 3 of the square root of x to the 4th over 4 plus 1/2 plus 1/4x to the 4th. But then this, and this is kind of the key step here, this part's going to factor just like this, except with the opposite signs in the middle. Right, so since these were minuses, I'm going to factor this as going to be x squared over 2 plus 1/2x squared. So really, I'm not even thinking about actually factoring this. I'm just looking back and saying like, oh, it's this, but with the opposite sign. Do I need to say more about that? I'm happy to if I need to. Or is that fairly clear what's going on there? So that's not really a good question. Let me know if you need more. So what usually ends up happening next is the square root and the square cancel. You do have to think about, because really the square root of something squared is the absolute value of that something. So you have to be like, okay, can I drop the absolute value? And the answer usually is yes. Right? If you're taking the absolute value of x squared over 2 plus 1/2x squared, well, first of all, those things are already always positive. X squared is always positive. X squared is always positive. So you can definitely drop the absolute value that wouldn't show up. So I'm just going to write this as the integral from 2 to 3 of x squared over 2 plus 1/2x squared. And I don't need the absolute value here because all of this stuff is already always positive. Does that remember all this on one page? So, sure, let's go. So here's the thing. The other nice thing about this is I already know how to differentiate this because this is essentially just the derivative of this, right? The derivative of x cubed over 6 was my x squared over 2, and the derivative of 1/2x was my -1/2x squared. So I know that when I anti-differentiate this, I'm just going to get back to this, except the middle sign is going to be a negative sign. Where to erase, I guess. Here, sure. So integrating x squared over 2, I know I get x cubed over 6. And integrating 1 over 2x squared, or 1/2 x to the negative seconds, I add 1 to the power divided by the new power, so I get 1/2 x to the negative first divided by negative 1, or -1 over 2x. Again, that's exactly the function I started with, except it's a minus sign in the middle instead of a plus. Right, I'll remind you, right, we were doing the function y equal to x cubed over 6 plus 2x. That's where we started. And so then it's just, the rest of this isn't bad. You're just plugging in numbers and calculating stuff. So I'm getting 3 cubed, which is 27 over 6, minus 1 over 6, minus, plugging 2, you get 8 over 6, minus 1 over 4. And it seemed like it was going to be nice to 1 over 4. I would probably put all the 6s in the denominator together. So I got 27 minus 1 is 26 6, minus 8 6. 26 minus 8 is 18 6, minus is plus 1/4. So I've got 18 6, which is 3 1/4. So 3.25, or whatever number of fourths, 13 fourths, I think. That's how long that piece of that function would be from x equals 2 to x equals 3. So, questions? I've got 1 or 2 more examples we can do, because there's slightly. So I would say most of the time, it's probably going to be something like this, especially if you see a function that's like something plus some other thing. And that's a very, very good sign that when you take the derivative and then square it, you're going to get the negative 1/2 in the middle, which means it's all going to work like this. There are a couple other things that can happen. Let me show you those. And please stop me or chime in if you have a question. Okay, so let's see what I've got here. I'm worried about you. Let me take a look real quick just to make sure this. I have one here that I feel like could be good, but maybe it's terrible. Oh no, that's perfectly fine. Great. Okay. So let's look at this one. So here's one of the ones that's like the parameterized version. So instead of being y as a function of x, I've got x and y both in terms of t. So I've got x equal to, or I like to write x of t is 1/3 t cubed. All right. And y of t is 1/2 t squared. And we're on the integral where t is between 0 and 1. And so in this case, it's slightly different. Right? The arc length is given by the integral from 0 to 1 of the square root of the derivative of this squared plus the derivative of this squared. That's dx dt squared plus dy dt squared. This one, the math isn't as ugly, I feel like. I feel like the other ones are usually a little bit less nice. So here we're going to get, so dx dt, so let's see, dx dt is going to be 1/3 times 3t squared. Sorry, so dx dt is just x squared. And dy dt is just 1/2 times 2t is going to be, oh, sorry, I shouldn't be x squared, it should be t squared. Apologies. And here the derivative is just t. So we're going to throw this into our formula. So I'm going to go from 0 to 1 of the square root of t squared squared plus t squared dt. Okay, so then we're going to simplify. So here we don't have the same kind of thing happening where there's a negative 1/2. So I have to kind of work on this. So let's see, I'm going to have the integral from 0 to 1 of the square root of t to the 4th plus t squared dt. What could I do next? Well, I see t to the fourth plus t squared. I think I got bit by something on the river, and my wrist really itches. I know I shouldn't scratch it, but okay. So what can I do about it? I can factor out a t squared. So I can write this as the integral from 0 to 1 of the square root of t squared times t squared plus 1. And then the square root of t squared is the absolute value of t, but since we're over 0 to 1, t is positive, so the absolute value of t is just t. So I can write this as the integral from 0 to 1 of t times the square root of t squared plus 1. And now, and so I really would like to hear an answer from you guys. What method of integration could I try to use to actually integrate this? Definitely use that, right? Because I can let u equal t squared plus 1, and the derivative of t squared plus 1 is 2t, and I essentially have that. So we would let u equal t squared plus 1, du is 2t dt, so 1/2 du is equal to t dt. So there's my 1/2 du. So I end up getting the integral from, well, actually, I get my 1/2 first, sorry. So I've got 1/2 the integral t dt, that's all right, that's my 1/2 du. And then the square root of t squared plus 1 is just the square root of u, or u to the 1/2. And personally, I would change the limits of integration. If t is 0, then u is going to be 0 plus 1, so u is 1. If t is 1, u is going to be 1 squared plus 1, which is 2. So we're going to integrate. We're going to get 1/2 times the integral of u to the 1/2 is u to the 3/2. Divided by 3/2 is multiplying by the reciprocal, which is 2/3. From 1 to 2. Since I change the limit, I don't have to go back to x. So I've got 1/3 times 2 to the 3/2 minus 1 to the 3/2. 1 in power is 1. And that's my final, not very nice looking answer. So that's how one of these ones would work. All right, one more, and then we will move on to something else. So you should be thinking about what you would like to see next. I'm imagining some sort of probability, not probability, I mean random variable stuff. But please, if you have things you want to see, let me know. I have to think about limits of integration on this one for just a second. Let's find the arc length. So the length, board feels like it's getting kind of wobbly here. All right, 1 second. Okay. The length of y equal to, I guess that one, yeah. Let's do cosine of x. Sorry, let me think for just 1 sec. Cosine? I gotta be careful here. Yeah, okay, yeah, sure, okay. Sure. On the interval from, no, I'm like, there's something dumb I'm forgetting here. Okay, sorry, not cosine. Y equals the natural log of cosine. I don't need the absolute values, those are totally unnecessary, sorry. On the interval from, I gotta make sure this isn't negative though, so let's stick in the first quadrant. Let's go on the interval from, let's say 0 to, I don't know, let's have more fun. Let's say pi over 4 to pi over 3. I don't want cosine to equal 0 because natural log of 0 is undefined. So I have to make sure I pick something right. I didn't pick pi over 2 because cosine of pi over 2 is 0. Okay, let's see what we get. I'm just going to throw this into the formula. It's going to be integral from pi over 4 to pi over 3 of the square root of 1 plus the derivative of this. Sometimes people just write this, right? The function derivative squared, which I know is messy, dx. All right, so what's the derivative of the natural log of cosine? There's a long answer and there's a short answer. Well, it's going to be 1 over the stuff. Then what do I have to multiply by? My tongue is making noises. Anybody? Anybody? I think I drank too much coffee this morning. Exactly. Negative sine of x. Now, we don't really want to leave it like this. I want to simplify it. Negative sine over cosine is just negative tangent. So when I put this in here, I'm going to get 1 plus negative tangent squared, and the negative is going to cancel out when you square. So I'm just going to get 1 plus tangent squared. This is going to equal the integral from pi over 4 to pi over 3 of the square root of 1 plus negative tangent quantity squared is positive tangent squared x. Does anybody know the trig identity for 1 plus tangent squared? Oh, I don't know if I've gotten to tell you guys my favorite way to remember the trig identity for tangent, 1 plus tangent squared. Normally this is more fun to say in class, but you know, in live person class. But oh well, this is what we've got. So the way I remember, and this is what a student told me one time. So I remember what the identity for tangent squared is well, here it is. It's 1 plus tangent squared x equals secant squared x. And what the student said is, I tan and get sexy. And I've never been able to forget it. Hopefully you won't either. So 1 plus tangent squared x equals secant squared x, or I tan and get sexy. So here's what's going to happen. 1 plus tangent squared x is going to become secant squared x. So I'm going to get the integral from pi over 4 to pi over 3 of the square root of secant squared x. Square root of secant squared is just secant. Now again, technically it's the absolute value of secant, but since we're in the first quadrant between pi over 4 and pi over 3, we know everything is positive in the first quadrant, so we can just drop the absolute value. Almost all the time, when you take the square root of something squared, it's usually in an interval where everything's positive, so you can almost always just drop the absolute value. This is going to be, oh no. Integral from pi over 4 to pi over 3 of secant of x. And I might have forgotten, do we know the integral of secant? It's okay if we don't. I feel like we might though. You guys remember if you learned it or not? Let me just say what it is. And if you don't know it, that's fine. It's probably not required. But here's it. So the integral of secant is the natural log of the absolute value of secant of x plus tangent of x. It wouldn't surprise me if Merckx had covered this. It also wouldn't surprise me if he didn't. So if this doesn't look familiar to you, I wouldn't sweat it too much. But it might be something. I guess I'll have to look at his kind of review stuff and see if it's something that's going to be on there or not. In either case, this is the antiderivative of secant of x. It's not pretty. It's the natural log of the absolute value of secant x plus tangent x. And then we'd evaluate it from pi over 4 to pi over 3. And so we're going to do that up here because it does simplify. So we get, plugging in pi over 3, the natural log of secant of pi over 3 plus tangent of pi over 3 And again, I dropped the absolute values because we know these are both positive. Minus the natural log of the secant of pi over 4 plus the tangent of pi over 4. And this just ends up being, let's see, secant of pi over 3 is 2, because cosine of pi over 3 is 1/2. It's just the natural log of 2 plus tangent of pi over 3 is the square root of 3 minus the natural log of secant of pi over 4 is it's square root of 2, because cosine of pi over 4 is 1 over the square root of 2. And tangent of pi over 4 is 1. So that would be your final answer. Again, I would say don't worry about if this integral isn't known to you. If it's not, the process is still what's important, right? We did the whole kind of, right, the square root of 1 plus the derivative squared, and we simplified and we're able to do it. Excuse me. So, not the final word, but the last thing I'll say about arc length today is that most of the time you're going to have something inside the square root that simplifies to just some quantity squared. Most of the time it's going to be because you have like a negative 1/2 in the middle. Sometimes you have some trig stuff going on where things simplify using a trig identity. Usually it's 1 plus tangent squared that shows up being equal to secant squared. Occasionally there'll be something more like this where you can just simplify and getting some sort of nice huge stuff or something going on. Okay. So what else should we talk about? I think we've said enough about arc length today. And actually, before we get going on to another topic, I just want to say a couple things. Thing one, oh gosh, sorry. Reminder that you can take this class pass no pass, and you can make that decision up until like the last day of class before finals, which I think is June. I want to say June 5th. I'm not positive on that date, but somewhere up until the last day of week 10. So if that's something you're considering, just remember that it is an option. Again, you should be sure to talk with if it's like a major class, you might need to talk with an advisor before deciding to do that. The other thing I wanted to say, which I think I talked about last week, just is that as far as 16C goes, for those of you that do need to take 16C, there's probably going to be a lot more support for that from the AATC during the summer versus the fall. So if you're internally debating whether to take 16C over the summer or the fall, I would probably push you in the direction of summer, just because, at least summer session 1, because myself and Sarah and Grant and Claire and Casey will all be more available in summer session 1. Summer session 2, we also have STEP to kind of help with and see how that's going to go. So we will be less available during summer session 2, but not completely unavailable. And there was a third thing my brain wants to say. Oh, and as far as finals week, when is your guys' final? For Merck's, I should say. When is the Merck's final? Do we know when the final is? I guess I could take a look too. When is the final? I imagine he said something about the final. I know you're correct, Denise. I did say I'll be more available to help with 16C during summer session 1, because in summer session 2 we have STEP online, which will definitely take up some of our time, and in fall we have a whole like the whole usual classes that we teach, and 16C is not one of the classes we typically teach during the fall. We're not scheduled to teach a co-class this fall, so definitely. My opinion is that you'll be able to get the most help with 16C in summer session 1. That said, there will still be help available during summer session 2 and during the fall. They'll just be less. Okay, and how much time do you guys have for your final? I'm just curious. Just want to see. Maybe he says something about it in the syllabus. I just don't remember if he if he gave you I think he just gives you like the usual amount of time, like an hour or 2 hours or whatever. And then I know I was reading about, I feel like, okay, so your guys' final is the 10th. Okay, sorry, I'm just trying to, so I'm definitely going to be available for you guys during finals. I'm just trying to think about when will make the most sense for me to be available for you. If there's any FAM folks here, I know he just sent out an email about your guys' final. Do I know if a comet class? I imagine you mean a co-class, Moonies. And yeah, so we don't actually offer co-classes during the summer, but what will be available, and in fact, I know we've already kind of set our office hours. All of the specialists will be available to help different classes during specific times. I know I've already set times to help with Math 16C in the summer. Let me see if I can find that Google Doc real quick to remind myself. 1 second. Not the document I wanted. Let's see. Let me go to my Google Drive. Darn, I don't know where Sarah put it. I'll just have to find it later and let you guys know. I know there's specific times during the summer. Like I think it's like Tuesday, Thursday from 1 to 3, or Monday, Wednesday, Friday. There's something like that where I'm available during certain times specifically for 16C. And I will definitely let you know about that before the end of or before summer session 1 starts, but hopefully sooner than later. So, okay, the Merck's midterm is the 10th at 8 a.m. Is anyone from FAM still here? Do you guys know when your midterm is? Yes, I can go.
Yeah. But we have like different times.
Okay, sorry, I missed the date. What was that?
June 5th.
June 5th? Mm-hmm. Oh, that's early, okay. Okay, good to know. All right, midterm is June 5th, okay. All right, so that's like before finals week even really starts. I don't know, Addie. I'm not sure if they're required to actually give you 2 hours or not. I could definitely try and look for that. But yeah, I'll look into that and see. I feel like usually finals are supposed to be 2 hours, but there might be some different rules and regulations in this atypical time we are having. Okay, I think that's all the things I wanted to say, just kind of business stuff. So talked about past and past, talked about summer session, 16C, finals. Yeah, I think we're good. Okay, so back to math. What other math things should we do? So I guess we start about probability stuff. It's probability, or not, I mean, I keep saying probability, I mean like the other stuff, the words, once again, challenging. I mean the discrete random variables and the continuous random variable stuff. So I know we did that example last time. Okay, fine. There we go. Sorry, here's the page that I had. So we were last time we talked about calculating some stuff for continuous, or sorry, for some discrete probabilities. And most of the time, if like in these classes, the thing they're going to ask you usually is to either calculate the mean or the variance or the standard deviation. Really, variance and standard deviation are the same calculation. It's just standard deviation taking the square root. So for discrete, when we calculate the mean, the expected value, and these are all notations of that mu or e of x or x bar. It's the sum of the x's times their probability. And some of these people write it like this, and these people write it as the sum of x sub I times p of x sub I, where I goes from 1 to some n. But the idea is you're just multiplying each value by its probability and then adding them up. And that's how you get the mean. And then the way you get the variance is by doing the sum of not x times p of x, but the difference between x and the mean squared times the probability. So you're looking at how far something is away from the mean times the frequency or the relative probability that happens, and then adding that all up. And then you can write it like this, or you can do it like this, where you have a subscript on the x there. And then there's another version of this, which is usually actually easier to calculate, which is the sum of x squared times p of x, and then it's all of that minus the mean squared. It's the same, and I know Merck's actually showed the work to show how you get from here to here. It's not really that big a deal. We could definitely show it if you guys want to, but the idea is that usually we calculate this to calculate the variance because it's easier. And again, if you have this, or you have it with the I equal 1 to n. Okay. So that's how you calculate the mean, the variance. And the thing about this is actually the same way you calculate the mean and the variance for, sorry, pen, this is the same way you calculate the mean and the variance, whether it's a continuous or a discrete one. It's just that if it's continuous, instead of using a sum, you use an integral. So for continuous random variables, the way we calculate the mean of the expected value is the integral of x times p of x dx over whatever limit of integration makes sense, right? Usually over the whole interval. And the way we calculate the variance, I'm not even writing the standard deviation because the standard deviation is just the square root of whatever you get for the variance. So it's the integral from a to b of x minus the mean squared times p of x. Or the alternative version is the integral from a to b of x squared times p of x dx minus the mean squared. And usually, especially for the variance when it's continuous, this second version is much more simple to calculate the variance for than the first version. So let's look at some continuous examples. We can also do some discrete ones, but I feel like we definitely did some discrete ones last time. It'd be good to do some that are continuous. And so just like, I should say, just like with discrete random variables where the probability should all add up to 1, that's also true for continuous probability. All of the probability should add up to 1, meaning in this case, if we're talking about an integral, right, the integral over the whole interval should end up equaling 1. So let's look at a continuous probability example. So let's see. The weight of a potato in pounds at harvest is modeled by the probability density function which often gets abbreviated as PDF. So if you see a math person say PDF, they probably mean a probability density function. By f of x is 3/14 times the square root of x on the interval where x is between 1 and 4. I feel like I'm not giving all the context. Okay, yeah. Okay, sure. So, right, okay, so sorry. So, right, so this is saying the probability that you'll have a potato of weight x is given by this. Now, the thing with continuous random variables is basically it's actually, there's like a 0 probability of a potato having a specific weight. Like if I said, what's the probability the potato weighs 1 pound? It's essentially 0 because there's an infinite number of possibilities between 1 pound and 4 pounds. So when we talk about continuous probability, you're usually talking about what's the probability of having a potato of a weight in a certain range. Right? You're not just saying a particular value, but a range of values. So let's actually first make sure it is a probability density function, meaning that the total probability should add up to 100% or 1. So previously you do the sum and show up to 1. Now we're going to say that the integral from 1 to 4 of 3/14 squared root of x dx, and that should equal 1. Also, here's what the function looks like. So if x is 1, I get 3/14. So maybe like about there. If x is 4, square root of 4 is 2, 6/14, so like double that. My function looks something like this. And what we're doing is we're going to find all the area. And that area should equal 1. The area isn't 1, it's not a PDF. It's not a probability density function. And oftentimes they'll have you like solve for some constant case so that it is a PDF. So let's see if I calculate this. Well, let's rewrite this as x to the 1/2. So I integrate this, I get 3/14 times x to the 3/2. And notice how I always leave a little space here, because I'm not going to divide by 3/2. I'm just going to multiply by the reciprocal, which is 2/3 from 1 to 4. 3 and the 3 cancel. 2/14 is 1/7. So I get 1/7 times 4 to the 3/2 minus 1 to the 3/2. 4 to the 3/2 is 8, because it's the square root of 4, which is 2, and then take that and cube it, which is 8. So I therefore have 1/7 times 8 minus 1, which is 1. So yes, it is a PDF. The total area under the curve is 1. There's a 100% probability of our potatoes weighing between 1 pound and 4 pounds. So let's move on to the next question, which is what's the probability of having a potato that weighs between 1 pound and 2 1/4 pounds? And then we'll do the expected value of the variance.
So it was a PDF.
Sorry. Go ahead.
I'm sorry.
No, you're fine.
So it was a PDF because it was equal to 1. Is that what you said?
So it's a PDF because the integral over the whole interval is equal to 1. I suppose there's more to it than that. So to be a PDF, this function has to be non-negative, right? F of x should always be greater than or equal to 0. No, you're really fine, Nicole. Sometimes I jump. It's really okay. It's fine. So to be a PDF, this function has to be non-negative. So no matter what, at least on the interval, right? So any value you plug in for x should give you a positive value or 0 out. And the second thing that has to be true is that the integral from whatever my limits of integration are has to equal 1. Just like for the discrete one, right? For the discrete probabilities, all the probabilities have to be non-negative, right? Greater than or equal to 0. And then all of the probabilities had to add up to 1. It's the same idea, just continuous instead of discrete. So hopefully that, but definitely go ahead. Feel free to say words. Please, I like to hear you guys' voices. Even if it sometimes scares me. Let me know if you have questions about that still, and I'll talk more about it. But the question I want to ask now is, what's the probability of having a potato weigh between 1 pound and 2 1/4 pounds? 2 pound potato sounds like it'd be pretty heavy. Okay, I never really want to use decimals here, so I would definitely change that 2 1/4 to 2 plus 1/4, which is 8 quarters plus 1/4, which is 9 quarters or 9/4. So to calculate this probability, right, I'm really just asking, right, here's 2 1/4, 9/4. I'm just asking how much area, right? The area is the probability. So to find this, the probability of, and often we write it like this, probably the x is the x is between 1 and 9/4. And for these continuous random variables, it doesn't matter if you say less than or less than or equal to, it's the same, since the probability of actually equaling 1 or actually equaling 9/4 is 0 as far as we're concerned. But usually we put the equal signs on there. This is just going to be the integral from 1 to 9/4 of the same function. The nice thing about this is we've already done the integral. Right? We know that the integral of 3/14 x to the 1/2 is 1/7 x to the 3/2, right? So we don't have to do that work again. We can say, okay, this is going to be 1/7 x to the 3/2 from 1 to 9/4. All right, so you definitely pick 9/4, so it'd be nice to plug in. So if I plug this in, I get 1/7 times, I like to factor constant, 9/4 to the 3/2, which sounds terrible, but it's actually not. Minus 1 to the 3/2. 1 to the 3/2 is just 1. That's not a 7, James. So let's see. So 9/4 to the 3/2, I'm just going to do each part separately. 9 to the 3/2 is the square root of 9, which is 3, and then cubed. 3 cubed is 27. 4 to the 3/2 is 8, because it's the square root of 4, which is 2, and then 2 cubed, which is 8. Minus 1 to any power is 1. I'm going to write it as 8 over 8. And 27 minus 8 is 19. So I get 19 over 8 times 1/7, which is 19 over 56, which is pretty close to 1/3. So there's about a 1/3 or 1956 probability that our potato weighs between 1 pound and 9/4 of a pound. There's something else I want to say here. And it does seem like a valid answer. The only thing that we should be looking for really here, right, I mean, it should look like, right, it definitely looks like that's probably about 1/3 of the area. It should definitely be something that is less than 1, right, because the probability should never exceed 1. All right, what else do we want to ask here? Yes. So the other question that I knew I was going to ask is, what's the probability that the weight of the potato is bigger than or equal to 9/4, but less than or equal to 4? And there's an easy way and a hard way to do this. The hard way would be to do the integral, right? To do the integral from 9/4 to 4 of the same thing, plug loops of integration. But the easy way is to say, well, look, that's just the rest, right? If I found that this area was what, 1956, and the total area is 1, this area here has to be the difference, 1 minus 1956. So we can calculate this as just 1 minus the probability that x is between 1 and 9/4. It's called the complement, or whatever's left over. Right, so if I want to find this, it's just 1 minus the probability of the other stuff happening. And that's going to be 1 minus 19 over 56, which is 56 over 56, minus 19 over 56. And 56 minus 19 is 37. And that's often to take, right? We talked about this, I think, last time with the flipping coins and stuff, where like you could find the probability of getting, 1, 2, 3, or 4 coins, or you could just say it's 1 minus the probability of getting 0 heads, I should say, not coins. So right, so that's kind of the idea here. Is you can, if you know one probability, you can find the other rest of it by just subtracting from 1, because they have to add up to 1. All right, let's find the expected value. So the expected value is going to be a somewhat more complicated calculation. And I guess my notation would maybe slightly, I wrote the integral of x times p of x. usually we're x times f of x instead of x times p of x. Same idea. So to find the expected value, it's going to be integral over the entire interval always of x times the probability density function. All right, so that's how we're going to calculate this. Okay, so I would definitely rewrite it. I would factor out the 3/4. Write this as the integral from 1 to 4 of x times x to the 1/2 is x to the 3/2. Okay, and now we're just going to do the usual thing. So we're going to integrate that. I'm going to get 3/4 times the integral of x to the 3/2 is x to the 5/2 times 2/5, 1 to 4. Simplify here, cancel a 2 here and a 2 here. So I'm getting, let's see, 3/10. I'm plugging in 4 to the 5/2 minus 1 to the 5/2. And so let's see, what I get here is, so 4 to the 5/2 is the square root of 4 to the 5th, which is 2 to the 5th, which is 32. So you get 3/10 times 32 minus 1 to any power is 1. So you get, I feel like I'm making a mistake. No, that's right, okay. So I get 3/10 times 31, so 3 times 31 over 10, which is 93/10. That seems wrong. I feel like I made a mistake somewhere. Let me double check my work. Where did I make a dumb mistake? Oh, I did. So it was actually a really dumb mistake. Somehow in the very beginning I wrote 3. So let me ask you guys first, how do I know I made a mistake? How do I know that this answer is really kind of off? What is 93/10 close to? Yeah. Does 9 make sense as the average weight for a potato that's between 1 and 4 pounds? It does not, definitely. So I definitely see this and like, oh, I must have made a mistake somewhere because my average value shouldn't be bigger than all of the values in my interval. And the mistake I made was at the very beginning, I wrote 3/4, so it's supposed to be 3/14. So when I cancel the 2 there, I should get a 7 in the denominator instead of the 2. So that should be not 3/10, but 3/35. So I end up with 3/35 times 31, which is 91/35. And that answer makes more sense because it's between 2 and 3. It's kind of like, it's pretty close to 2 2/3. And the thing that you should know about the expected value, or also known as the weighted average. So if I look back at the picture that I had drawn, 2, 3, 4, and at 1 we have, oh gosh, 1, the 14th is so small. Double that. So my region looks like this. Pretend. And 91/35, or 2 23/35. Yep, it's pretty close to 2 2/3. That's like 1, 2. It's like about here. So that's where the weighted average is. And what the weighted average is, or the mean is, or where they get extra. So the x comes from the formula, Nicole. So remember how when we talked about like the for discrete, the expected value is given by the sum of x times the probability function p of x. It's the same thing for continuous random variables. You're just using an integral. So for continuous, the expected value, or the mean, is given by the integral of x minus p of x, except it's really supposed to be f of x, not p of x. Same idea. And really it's because you're saying, oh, I'm taking each value that the potato can have, right? Each weight the potato can have, and then multiplying by the probability. So the ones that have lower probability get counted less, and the ones that have greater probability get counted more. And also the bigger values contribute more. So what we're seeing here, or hopefully seeing, the idea is that this spot here, this expected value equal to 93/35. This is where this area would balance, right? Even though there might be more area on one side, it's not where there's half the area on one side and half the area on the other side. It's where the area would balance, like if you were thinking of it as like a seesaw or something. This is the point here where this area concentrated here, even if it's a little bit more or less, and this area concentrated here, even though maybe it's a little more spread out, they would exactly balance to kind of like how if you're on a seesaw, a heavier person closer, a lighter person, no, the length is more, sorry, a lighter person or a lighter weight further out can balance a heavier weight closer in, because how far away it is contributing, is part of the, what's the word you're looking for, is part of the weighted average, right? It's saying, oh yeah, we've got this really big distance contributing to how much it's kind of pushing it this way or that way. I feel like I'm not doing a great job of explaining this, but that's kind of the idea with the expected values, that you're finding where the middle, not the middle, well, it's one measure of middle, but you're finding where things would balance. This is different from the median, which we could calculate. The median is actually where you have half the area on one side and half the area on the other side. Calculating the median is kind of a pain, but I suppose we might as well do that, because so actually let's do two things. Let's calculate the variance, and then we'll talk about calculating the median. So the variance is not nice. Well, let me show you the ways we can calculate the variance. We definitely need to know the mean to calculate the variance. So the mean being 91 degrees. So we can either calculate the variance as this integral of x minus the mean squared times f of x, which in this case would look like the integral from 1 to 4 of x minus the mean we just found, which is 91/35 squared times the probability density function, which is 3/14 times the square root of x. And that looks like a big old hot mess. Or the way we should usually calculate it is the integral from a to b of x squared times the probability density function. And then outside of the integral, subtract the square root of the mean, which in this case would look like the integral from 1 to 4 of x squared times 3/14 times the square root of x. And then you would subtract 91/35 squared. And hopefully you guys can see that this is much nicer. If you do it this way, you have to multiply this out and get your x squared minus 2 times this times x plus this squared all times that. So you're gonna have 3 terms you have to deal with integrating. Whereas this one is just gonna be one thing to integrate. So you definitely want to use, oh, is it 93 or 91? Good question. I might have lost yeah, 93. Thank you. Good catch, Sophia. Totally 93. Yeah. Yeah, but this one's gonna be much nicer because it's just one thing to integrate. So I'm gonna do it this way. I'm gonna bring out the 3/14, not 3/4, 3/14. And I have x squared times x to the 1/2, which is gonna be x to the 5/2, 1 to 4. Dx minus whatever that terrible number is. And so doing this, it's not going to be pretty. We're going to get 3/14. The integral of x to the 5/2 is x to the 7/2 times 2/7 from 1 to 4 minus this garbage. And then simplifying, let's see, we can cancel a 2 here and a 2 to 7. We got 3/7 squared, which is 3 over 49 times 4 to the 7 halves minus 1 to the 7 halves, which is 1, minus 93 over 35 squared. This is not nice. Let's see, 4 to the 7 halves is the square root of 4 to the 7th. So 2 to the 7th is 128. So 349 times 128 minus 1 is 127 minus 93 over 35 squared. And I would probably, yeah, that's where Grant stopped too. He's like, yeah, that's gross. So you get some number. It's, oh, how about 40? Yeah. 49, not 14. So, yeah, so you get 381 over 49 minus this gross thing, which I would just get out of the calculator at that point. And that's how you would calculate your variance here. And then if you wanted to know the standard deviation, you would just take the square root of that. So the standard deviation, if you use the sigma for, would be the square root of whatever this is here, which is still not particularly nice. Okay. I do feel like we might as well talk about the median since we're already here. So to calculate the median is to say you want to find the place, and I honestly don't know. It's probably, I don't actually know if it's bigger or smaller than the mean in this case. It can be either way depending on what you've got. But the way you calculate the median is you're looking for the place. Let's just say it's over here, even though it might actually be on the right. We should call it lowercase m, where half the area is here and half the area is here. What you do is you take your integral, say, oh, I want to integrate this function, and I want the integral from 1 to the median to equal 1/2. Or you could also equivalently say the integral from the median to 4, right? This is an m points 1 and 4. You could say that has to equal 1/2. And usually just pick whichever one feels like it's going to be easier to plug the numbers in. I would definitely pick this one because it's easier to plug in 1 when we integrate than it is to plug in 4. But either one would be fine. So I'm going to do this. I'm going to do the integral from 1 to m of 3/14 times x to the 1/2 dx. I'm going to set that equal to 1/2. So then I'm going to integrate this, and it's not going to be lovely. I'm going to do the integral of 3/4 x to the 1/2 ended up being, I don't remember what I think it was 1/7. It was 1/7 x to the 3/2. I think. Now I'm not sure. Let me check. 3/14 2/3 x to the 3/2. Yeah, the 3's canceled too. Yeah. 1/7? Sure. And then we're going from 1 to m, and that's equal to 1/2. Then we plug in our limits of integration. I'm going to leave the 1/7 factored out. So I'm going to have 1/7 times m to the 3/2 minus 1 to the 3/2 is just 1 equal to 1/2. And then we're going to solve for m. So multiply both sides by 7. So m to the 3/2 minus 1 equals 7/2. Add 1. So m to the 3/2 equals 7/2 plus 2/2 is 9/2. And then take the 2/3 power of both sides to get m equal to 9/2 to the 2/3 power. And I would like to actually know approximately what that number is. So let's take a look real quick here. So 9/2 to the 2/3 power is about 2.72. Which is probably bigger than 93/35. Yeah, 2.65. So actually, sorry, our median was like, I mean, they're pretty close to each other. Our median's like right here. And not that that picture is doing me justice, but I'll say again, the median is the value where half of the area is to the left and half of the area is to the right. Or when you're talking about, like, again, I think we talked about this before, when you're talking about, for example, household income, the median value is the value where half of the people make more than that and half the people make less than that. Whereas the average value, what we know what the average value is, the average is, it gets really skewed upwards because there are some people who are really, really high earners. So that's kind of the difference between median and mean. The median is definitely more difficult to calculate usually. The mean is usually more straightforward. And I guess we're out of time. It's 10:21, so I should probably stop talking. So yeah, I got things to do for you guys. Make sure you fill out the attendance form in case you haven't already. One last time, here's the link to the attendance and the tutoring and the end of the quarter evaluation. Also remind you guys I do have office hours today from 2:30 to 3:30. So if you have questions, feel free to drop on by. And I think that's all I've got. Hang in there. You got 2 weeks left. You guys can make. Oh yeah, and then yes, yeah, the office hour schedule. I will definitely. I know I've got it somewhere. I just don't know exactly where it is. So I will definitely. I'll probably post it as an announcement or something, and I will also email it. Office hour schedule. Yeah. Got it. All right. I'll see you guys on Thursday. Take care. We don't know, we don't have it set for summer session 2 yet, Addie. We do plan on having some availability, but we don't know exactly because we're still trying to figure out what we're going to be doing for STEP exactly. So there will be times for summer session 2. We just don't know what they are yet. All right. You're welcome. I'm going to end the meeting. We'll talk to you guys later. You're welcome.